In the previous lecture, we started the discussion on the MOSFET, that is the metal oxide semiconductor field effect transistor, which we claimed was supposed to be the building block for most of the modern day logic circuits. So, in the previous lecture, in that discussion, we also saw that what is the physics behind the MOSFET and what are the regimes of operation. So essentially, what we saw was that a MOSFET has some characteristic properties, that it has four terminals, although one of the terminals is not always shown. So the remaining three terminals are the drain, gate and source. So over there, we said that every MOSFET has a characteristic property called as a threshold voltage or VTH. So this sort of decides how the MOSFET normally behaves. So if we say that the gate voltage is more than the threshold voltage, or let us say the gate to source voltage is more than the threshold voltage, we say that the MOSFET is on. And when the VGS is less than VTH, the MOSFET is off. This is obviously for the NMOS transistor. For the Pmos, it is the opposite. So for the Pmos, which essentially works in just the opposite way the NMOS does, the NMOS has electrons as majority carriers and the Pmos has holes as the majority carriers, which is built on an N-type substrate. So whatever is applicable in case of the NMOS, it's just the opposite which happens for the Pmos. But the principle remains pretty much the same. So therefore, for the Pmos, we say the VGS should normally be less than VTH. In that case, it is on. And when VGS is more than VTH, it is off. Just the opposite. So normally for NMOS, the threshold voltage is positive. And for Pmos, the threshold voltage is negative. This is normally what the difference between the NMOS and Pmos is. Now once we say, let us say for the NMOS, once we say that the VGS is more than the VTH, we say that the transistor is on. Now when we say on, what it means is that the bridge between the drain and the source has been formed. And that bridge is the bridge consisting of the charge carriers. In case of NMOS, it is the electrons. So what effectively happens is that we saw even when the transistor is on, there are two ways in which it can behave. One is called the linear regime, the other is called as the saturation regime. So if the MOSFET is on, it can be either in the linear regime or in the saturation regime. So what effectively happens is that both of these have their own uses. So we saw in terms of graphs what the current looks like as a function of the voltage. We saw that the graph is little different in case of the linear regime. It's different in case of the saturation regime. So obviously both of them have their uses. So in case of the NMOS, we saw that if you are plotting the drain current as a function of the drain to source voltage, effectively what it looks like is that it increases quadratically and then sort of becomes constant. So therefore, this is the saturation and this is the linear. Okay, so this is what it looks like. Now, in both cases, the MOSFET is on. There's no doubt about that. But the way it behaves is little different. So effectively what is happening is that if we have an NMOS, this is the drain, this is the source, this is the gate. So what we are looking at is the drain current. So in such case, what is happening is that if I am plotting a graph of ID versus VDS, and VDS would be this quantity, I am still talking about an NMOS. So when I'm plotting a graph of ID versus VDS, what I'm seeing. Normally, any voltage current graph would give me information about the resistance of the device between the two terminals in question. So immediately what I can see is that in the saturation region, no matter how much you increase the voltage, the VDS, the current remains constant. So in this case, I can say that in saturation, since the current is pretty much constant with change in voltage, the resistance between the drain to source tends to infinity. Likewise, if I take a derivative of ID versus VDS, it will be 0, which indicates 0 conductance. So therefore, the resistance is infinite. Now what is happening is that you will see that in this case, when it is in the linear region, the RDS is finite. So that is like saying the resistance is no longer infinity, because with change in VDS, the ID also changes. But what we are seeing is that as we decrease VDS more and more, the slope of the graph essentially increases, which means that as VDS reduces, the ID essentially, the change in ID essentially increases. So here the RDS essentially decreases in this region. And over here, as you come more and more towards saturation, the RDS increases. So therefore, why am I talking about all this? I am talking about all this because this notation must have given you some kind of a hint. I am trying to use the MOSFET like a switch. So if VGS is more than VTH for an NMOS, I want it to be on. Now when the switch is on, what should be the resistance for the switch? The resistance for the switch should be as less as possible. So therefore, we always try to ensure that we have the switch on, and that too in a region where VDS is pretty low. So now how that is managed is a different story. Let's not get so much into that. At the same time, we need to ensure that when VGS is less than VTH, the transistor is off. That is, the drain current should be 0. And that we know happens because when the VGS is less than the VTH, the bridge between the drain and the source is not formed. So therefore, no amount of current can flow between the drain and the source. So this is how we normally look at the MOSFET. So therefore, let us now look at this. Let us now look at how we can use the MOSFET as a switch. So therefore, if I have, let us say, an NMOS and I have a PMOS. As you know, the symbols are something like this. I'll say this is gate. The drain and source are interchangeable, so you can write them any way you want. For PMOS, the gate is indicated with a bubble. Now the reason for the bubble is because of the way the on and off conditions are opposite for the PMOS as compared to an NMOS. So effectively, what happens is that if I say the VGS is high, that is, if it is more than the VTH, this is on. And here, if VGS decreases, or that is like saying it's less than VTH, in this case, the PMOS is on. This is what we had described. So therefore, when the PMOS is or NMOS is on, essentially they look like a closed switch. So suppose I can say that each of these transistors are something like a switch where we have a bridge between the drain and the source. And the on-off control of the switch lies with the gate. So effectively, the gate voltage, which effectively is represented as a gate to source voltage, controls the switch whether it is on or off. In case of the NMOS, if this voltage increases, this becomes on, and when this voltage decreases, this becomes off. In case of the PMOS, when this voltage decreases, the switch becomes on, and when this voltage increases, the switch becomes off. So therefore, it is as simple as this. All we need to ensure is that the VGS is more than the VTH. Now generally, the question now you may ask is that how do we ensure that the VGS can be more than VTH? So normally, if we are going to ponder upon this question, we have to first ask ourselves, what is the logic level that we are considering? So therefore, suppose I say logic 1 corresponds to 5 volts and logic 0 corresponds to 0 volts. This is what the standard we are keeping. So generally, for MOSFETs which are designed to work with maximum of 5 volts, the threshold voltage, now I will write it as mod VTH, because remember what I said? Well, I didn't say it so far, but probably, oh yeah, no, I did indeed mention it. So not for the VTH for the NMOS is positive and the VTH for the PMOS is negative. So since the devices we can consider as identical, so what I will represent is something called as mod. Generally, the mod VTH for this kind of MOSFETs is anywhere from 1.5 to 2 volts. So therefore, any voltage above this you give, it might be recognized as a 1 for an NMOS and opposite for the PMOS. So therefore, the question now that we need to ask ourselves is, how do we make simple logic gates using these transistors which apparently can act like switches? So let's see. Let's suppose I have two voltages which I am supplying. One is a 5 volt supply, the other is ground or 0 volts. So effectively 5 is logic 1 and 0 is logic 0. Now let us say I have some input, let me call it as VA. Let's start with first things first. Let's say we have something very simple, that is a single voltage input, and the system that is also having a single output VY. Now what we can see is, let's say I want to feed this VA to the gate of one NMOS and one PMOS in this fashion. Let's say this is a Pmos and this is an NMOS. Let me label it. Although the presence of the bubble over here should give you a good idea. So this is how I am claiming my circuit to be. Now, first things first. Let's say we'll take case 1 when VA equals 5 volts. Now, if VA equals 5 volts, let us look at what is the voltage reaching at the gate of each transistor. So, the gate of the PMOS gets 5 volts and the gate of the NMOS gets 0. Now let us say that for some we are defining this as the source for the NMOS and this as the source for the PMOS. And this is the gate. I am defining the source because in general source and drain can be interchangeable. So in this case, let us see what is happening. For the PMOS, what is the VGS? VG is 5 volts and VS is also 5 volts. So therefore VGS is 0. Now, will this be on or off? Well, I think I made a very small mistake when I was mentioning about the switches. The PMOS will be on if VGS is less than mod VTH. Let's put that mod thing into question. So let us say the VTH of the Pmos is minus 1.5 volts. So in this case, indeed the VGS is less than mod VTH. This condition is met. So therefore the Pmos will be on. The Pmos will be on. What about the NMOS? The gate voltage, oops, I made a mistake. There is no need for the mod condition. The mod is not needed. So therefore, in this case, what is happening? VGS is 0. And in this case, if the VTH is minus 1.5 volts, the VGS is more than that. So therefore, the VGS is now more than VTH, which indicates that the Pmos is off. Just be very careful with this. The NMOS, on the other hand, the gate voltage is 5 volts, source voltage is 0. So the VGS is now 5 volts. Now VGS, what is happening? It is more than VTH. Now VTH for the NMOS is positive. So therefore, let us say it has a threshold voltage of plus 1.5 volts. So in this case, VGS greater than VTH is satisfied. So that means the NMOS is on. So in this case, what is going to happen? The 5 volt is over here. The Pmos is going to behave like an open switch. But the NMOS is going to behave like a closed switch. And this is Vy. Now, when we say closed switch, we assume that it's an ideal switch. The transistor is operating in the linear regime with very, very low on resistance. So therefore, what will be Vy? In this case, you can see Vy is connected to ground. So therefore, in this case, Vy is 0. So when the input is 5 volts, the output is 0. Let us look at the converse. Let us say when Va is 0 volts. In that case, let's again draw the circuit. So over here, this is Va, this is Vy. So if Va is 0 volts, let's again write for the NMOS first. The Vg now becomes 0 and Vs is 0. So VGS is 0 volts, which is less than VTH. So that means the NMOS is off. Now for the Pmos, Vg is 0 volts, Vs is 5 volts. So VGS is minus 5 volts, which is indeed less than VTH if you assume that the VTH is minus 1.5. So that means the Pmos is off. So therefore now the circuit will look like this. The Pmos will now be a closed switch while the NMOS will be an open switch. So Vy is connected to 5 volts. So in this case, Vy is exactly 5. So what we are seeing is, if you now draw a table showing Va and Vy, in that case, Vy will be 5 volts when Va is 0 volts and Vy will be 0 volts when Va is 5 volts. This is what we just proved. So therefore, this is equivalent to a NOT gate. This is equivalent to a NOT gate, also called as an inverter. Of course, this is not the same inverter which we use in our domestic power supplies in our home or wherever. That is a totally different inverter. But here it's called inverter because it essentially inverts the logic. So we saw how using one NMOS and one PMOS we built something that is as simple as a NOT gate. Let us take some more examples. Well, let us now go over to having two inputs rather than one. So therefore, some intuition tells me that going by the way we looked at the NOT gate, we will now need more number of MOSFETs. If one input needed one NMOS and one PMOS, two inputs will need two NMOSs and two PMOSs. Okay, so let us see how we can do this. Again, let us say this is my 5 volt line and this is the ground line. Then, if I have two transistors in parallel and these two are PMOSs and I have two transistors in series which are NMOSs. So let us say I have two inputs VA and VB. Let us say this is VA and this is also VA. So each input will go to one NMOS, one PMOS. This will be VB and this will also be VB. Alright? And this junction between the NMOSs and PMOSs will be my VY. Now how would this work? Let us now simplify our analysis. Let us not trouble ourselves with the knowledge of VTH. Whenever we say, we say we will analyze this kind of a diagram, this kind of a circuit, let us only look at the gate voltages. Because now we know that for an NMOS, if the gate voltage is high, it will be on. And for a PMOS, if the gate voltage is low, in that case it will be on. So therefore, let us again write a truth table. 0 and 0. So when VA and VB are both 0, what will happen? Before writing VY, we will write a column called transistor, which will indicate what is the status of each transistor. So when VA and VB are both 0, these two are getting 0. So therefore, because the NMOS is getting 0, they both will be off. Both NMOS off. Now what about the PMOSs? Both are getting 0. In this case, since both are getting 0, both will be on. Both PMOSs are on. So in this case, these two will act like open switches and these two will act like closed switches. So therefore, VY will be a direct connection between 5 volt and itself through two parallel paths. So therefore, VY will be 5 volts. Let us now look at 0 and 5 volts. Suppose VA is 0 and VB is 5 volts. VA is 0, VB is 5 volts. So if VA is 0, this top NMOS will be off and this NMOS will be on. So we'll say VA NMOS off, VB NMOS on. Now what about the PMOSs? VA is 0, so this PMOS will be on. But VB is 5, So this NMOS, so this Pmos will be off. VA is 0, this Pmos will be on. VB is 5, this Pmos will be off. So therefore we will say VA Pmos on, VB Pmos off. Once again we can see that because VA transistor is off, this will act like an open switch. So there will be no path to ground. But since VA is on, again there will be a path between Vy and 5 volts. So therefore the output will also be 5 volts. Now when VA is 5 volts and VB is 0, I can immediately see that the converse will happen. Now the VA transistor NMOS will be on, VB NMOS will be off, and VA Pmos will be off and VB Pmos on. So what we are seeing again, since this transistor is off, there will be no connection between Vy or ground. But now since VB Pmos is on, there will be a direct connection between Vy and 5 volts. So therefore the output will be 5 volts. Now when both inputs are 5 volts, what will happen? When both inputs are 5 volts, it's very simple. Both the Pmoses will be off. But this time both NMOSes will be on. Therefore, it will provide a direct path between Vy and ground. Therefore, the answer will be 0 volts at the output. So in this case, we will say both NMOS on and both Pmos off. This will be 0 volts. Now, does this truth table remind you of something? 1110? Yes. This is a NAND gate. So using 2 NMOSes and 2 Pmoses, we have made a NAND gate. We analyzed each of these input configurations by looking at which transistor is on, which transistor is off. We are essentially treating the transistors like switches. Now, let us look at one more case. Let us look at one more case. Again, we have 2 inputs. So therefore, again we will need 2 NMOSes and 2 Pmoses. But now let us reverse that configuration. Earlier we had 2 NMOSes in series and 2 Pmoses in parallel. Now let us do the reverse. Let us now have 2 Pmoses in series and 2 NMOSes in parallel. So the analysis would now just be the opposite. So initially, when both inputs are 0 volts, both of these Pmoses will be on and both the NMOSes will be off. So therefore, there will be a direct connection between 5 volts and Vy. So therefore, Vy will be 5 volts. When Va is 0 and Vb is 5, When VA is 0, VB is 5. The VA PMOS will be on and the VB NMOS will be off. But the VA NMOS will be off and the VB PMOS will be on. So let's write it. So therefore, this connection is broken. But because this VB NMOS is on, there will be a direct connection between VY and ground. So therefore, output will be 0 volts. Likewise, you can also prove for the third case, and you will see that the output will be 0 volts. Now, when both VA and VB are 5 volts, both the PMOSes will be off and both the NMOSes will be on. So once again, you will have VY connected to ground through two parallel paths. So here it will be both PMOS off and both NMOS on. So in this case, there will be direct connection to ground and the answer will be 0 volts. So what you are seeing at the output 1000, does this remind you of something? This is the NOR gate. This is the NOR gate. Is that fine? Now, with this we saw how to very easily make a NOT gate, a NAND gate and a NOR gate. So once we have all these universal looking gates, we can actually make any gate that we want. As we know, NAND and NOR are universal gates. So using this, you can make any circuit that, or any logic gate you want. Now there are certain interesting features which we need to see. There are certain interesting features of our discussion which we need to see. First and foremost, what is the name of this technology? This technology, which we saw, is called as CMOS technology, also called as Complementary Mosfet. Because what is happening, or rather why this name is coming? As you know, complement is something which we call for opposing cases. Normally we say the complement of A is A bar, or the complement of A bar is A, as we know from our Boolean theorems. So the question now is why this is called so. So what we are seeing is that irrespective of how many inputs are there, I have a 5 volt line and I have a 0 volt or ground line. And I have two kinds of networks. On top, I have a Pmos network. And on bottom, I have an NMOS network. And here what we are seeing is the output Vy. What we have seen so far in our discussions is that never it so happens that both the top network and the bottom network are on together, or both of these are off together. So therefore, network and NMOS switch network, both on is not possible, or both off is not possible, because both of these are critical cases. If both of these become on, then these will be closed switches and you will give a zero resistance path between 5 volts and ground. And that is disastrous. It's like saying I'm connecting the plus of a battery to its minus. That can never happen. Now, if both are off, this Vy would be an undefined position. It will, there will be no defined voltage at Vy. So, and that should never happen. So, if both are off, Vy becomes undefined. Vy becomes undefined. And if both are on, Vy will become 0, definitely. But the current that is being drawn from the supply would be extremely, extremely high. And that would cause a failure in the power supply itself. So this we call as supply failure. Both of these we don't want. But the consequence of this discussion is to imply that any point of time one will be on. Thereby giving Vy a connection to either 5 volts or 0 volts, but not both of them together. So it is like when the NMOS network is on, the Pmos network is off. Or when the Pmos network is on, the NMOS network is off. Therefore, the name complementary MOS. Therefore, the name complementary MOS. One more thing to note about this, which is very interesting, is that number of inputs in the system, let's say n, or let us say small n, that means n number of NMOS transistors and n number of Pmos transistors also. That is the rule. If you have n number of inputs, you will need n number of NMOSs and n number of Pmos's, which implies 2n number of transistors. 2n number of transistors. Is that fine? So this is what the CMOS technology looks like. And most modern day logic circuits, in one way or another, they are dependent on CMOS. And CMOS is one of the most successful and widely used logic design approaches that we have today. Now, the good thing about MOSFETs, when you compare them to bipolar junction transistors, is that when you keep reducing the size of the MOSFET more and more, its properties don't change so easily. Its properties don't change so easily. That is, it can still operate, its linear regime, saturation regime will still be there. When you make the MOSFET smaller and smaller, its threshold voltage will reduce, its power consumption will reduce, but at the same time, it will not deviate from its properties. It will never ever deviate from its properties. Well, there will come a time when it will deviate, but the degree to which you can make it small is extremely large. Let us see an example. So in the 1980s and 1990s, this 5 volt logic system or logic standard, where 5 volt corresponds to logic 1, they used to make sizes for each of these MOSFETs. So the size of the MOSFET was usually indicated by the length. If you recall, length is the distance between the drain and the source. So this is what it was. This is the length. So as I reduce my length, other dimensions will also reduce. So for 5 volt logic standard, a very popular value of L that was used was 500 nanometers. That means half a micrometer, which is very, very small. You cannot see it with your naked eye. So this is how it was. So the length was 500 nanometers. This was in the 1980s and 1990s. In the late 90s, they came up to something called as a 3.3 volt logic standard. So in this case, a very popular value of L that was used was 250 nanometers. So the transistors were made even smaller, to be half by precise. To be precise, it was half a reduction. Then you had 1.8 volt logic standard. Where the L was 180 nanometers. This was in the 2000s. And they are still used today. All of these are still used today. But this was much later as compared to the earlier ones. Then you had a 1.2 volt logic standard. Over here the length was generally from 90 to 130 nanometers. This came in around late 2000s. And so on and so forth. It kept reducing and reducing. Today, if you look at very fast logic circuits, their lengths are as small as latest ones are, unless I'm mistaken, they are anywhere from 14 to 22 nanometers. Intel is even experimenting with 7 nanometers and lower. So this is the way in which logic standards have evolved. Now in all of these cases, this indicates logic 1. And for all of these, logic 0 is 0 volts. So lesser the logic standard, lesser will be the power consumption, lesser will be the size of each transistor. And therefore, on a piece of silicon, you can accumulate more and more number of transistors and make really complex and high performance logic circuits. So in today's particular lecture, we saw how we can use the MOSFET like a switch and how we can build different logic circuits. We saw, to be precise, the NOT gate and the universal gates NAND and NOR, how to make them using MOSFETs, and in particular this technology is called CMOS technology. And thereafter we just saw how much the CMOS technology has changed and how much it has improved over the years, where the transistors are essentially becoming smaller and smaller without losing too much of their original properties.